Okay, we're going to finish up chapter 10, which is our last chapter in the course. So we're going to finish talking about solids and liquids. So we ended with this slide, but I can't remember exactly what I said, but I think I wanted to go back and talk about this example. So this example asked which will have the highest vapor pressure of these compounds. And so we want to explain it based on their intermolecular forces. And I can't remember what I said, but I feel like I said it wrong, water relative to the other one. So we can like pick out which will have the highest and which will have the lowest vapor pressure. So the highest vapor pressure will be the system that has the weakest intermolecular forces, because that means the molecules aren't held as tightly in the liquid phase and you'll have a greater pressure at any temperature. So when you look at this, ethanol, ethylene glycol, and water all can hydrogen bond, but diethyl ether is a dipolar molecule, but it has a very weak dipole. If you actually were to draw this structure, you'd see that with the oxygen in the middle, it has a very weak dipole. So that should have the highest vapor pressure because it has the weakest intermolecular forces. And then we want to compare the three systems that have hydrogen bonds. So we can think about first, ethanol is different from ethylene glycol and water in that it can only form one hydrogen bond, whereas water and ethylene glycol can form two. So that would mean ethanol has weaker intermolecular forces, so it will be next to diethyl ether. So diethyl ether has the highest, ethanol the second. And then when you compare water and ethylene glycol, they both can form two hydrogen bonds, but ethylene glycol is bigger, so its London dispersion forces should be bigger than water. So it should have stronger intermolecular forces than water. So it should go diethyl ether has the greatest, ethanol has the second greatest, then water, then ethylene glycol in terms of the greatest vapor pressure. Okay, so now we're going to talk about boiling points and some of the physical changes. So boiling point is by definition, it's when the vapor pressure of a liquid increases enough to equal the external atmospheric pressure, and then we call that the boiling point. So when the temperature at which a liquid boils depends on the pressure above it, that's always true. Because it's when the vapor pressure equals the external pressure. So if you're on top of Pikes Peak, water is going to boil at a lower temperature because the atmospheric pressure is lower than it is down here. So the normal boiling point of a liquid is the temperature at which the liquid boils when the pressure above the liquid is 1 atm. So for water, that's 100 degrees. And that's just a definition, what it means to say the normal boiling point. And during the boiling process, temperature remains constant. So we'll think about that. So variations in atmospheric pressure will change the boiling point. We basically just said that in this slide. So at high altitude, atmospheric pressure is lower, so the boiling point is lower. This is, I am going to sneeze. This is a graph of boiling points of liquids. And so what can we, well, we can look at these if we compared all their normal boiling points. So the temperature at which they boil when atmospheric pressure is equal to 1 atmosphere. So that's the dotted line. It's about 105 kilopascals. So ethyl ether has the lowest temperature, then ethyl alcohol, then water, then ethylene glycol. And so that is exactly the set of molecules I just went through in that example that I wanted to correct. And so ethylene glycol has the strongest intermolecular forces, therefore it has the highest boiling point, then water, then ethyl alcohol, and ethyl ether should boil at the lowest temperature because it has the weakest intermolecular forces. So this is an equation called the Clausius-Clapeyron equation, which allows you to relate the vapor pressure at different temperatures for a substance. And it's a logarithmic relationship, and it depends on the delta H of vaporization of the substance. So this is an equation you would learn how to derive in physical chemistry. Right now, we just have to believe that someone knew what they were doing and that it truly is a logarithmic relationship between vapor pressure and 1 over temperature. So temperatures must be in Kelvin. R makes most sense to use in joules because your delta H is probably going to be in joules. But whatever units you have for your delta H, you'd want to put your R in. This is just showing you that when your sweat evaporates, it cools your body because it takes heat to evaporate water. Okay, so this is talking about the process of melting. So that idea that as something melts, the temperature stays constant. So let's say you take some solid ice and you start to heat it up. As you add that heat, the temperature is going to rise. When you get to 0 degrees, which is the normal melting point of ice, then while the ice melts, you're going to be adding heat, but the temperature won't change because that energy that you're adding will go into breaking the intermolecular forces, in this case, the hydrogen bonds. And so then when all of it becomes a liquid, then that liquid will start to raise in temperature again as you add more heat. This is a demo I always do in class. It's a pretty one. It's solid iodine sublimes. And so you can see the really pretty purple gas. And you can also see how it depends on temperature. If I put it in warm water, that gas up above will have a higher pressure. And so it'll be a more deep purple. And this is showing you an example of Hess's law. If sublimation is going from solid straight to gas, you could do that in 2 steps by first melting the solid. So that's fusion, and then vaporizing it. So the delta H of sublimation should be equal to the sum of the delta H of fusion and the delta H of vaporization for any substance. And this is how we determine where something boils and melts. So if we didn't know, if we had a new substance and we're trying to figure out what are its temperatures for melting and vaporizing, we'd do a heating curve. So on the y-axis, we have temperature, and on the x-axis, we have how much heat we've added. Could be in joules or calories. Sometimes it's time if you're using a heater that's producing heat at a constant rate. But you see, every time it plateaus, we know there's a phase transition because that's a temperature at which we put heat in on the x-axis, but the temperature stays constant. So each of these plateaus allows us to determine when the substance melts and when the substance vaporizes. So in this case, it's water. So you can use that information that you get from heating curves to draw a phase diagram, which is simply a diagram that shows you the relationship between pressure and temperature and what phases are present. So if we make heating and cooling curves, so this curve could also, you could do it the opposite way. You could heat the water up until it's a gas, and then you could slowly cool it off. So it's the opposite of a heating curve, but you get the exact same information. So during phase changes, the temperature remains constant. So we learned that from a cooling curve. If energy is being absorbed in the phase change, then all the energy is used to break the intermolecular forces and not increase the temperature. I've said that already, so hopefully that makes sense to you. If energy is being released during the phase change, then all your released energy is coming from the formation of those intermolecular forces, and it won't decrease the temperature. So if you're going up or down in energy, phase transitions will always be located at temperatures at which at plateaus where the temperature remains constant as you're either putting heat in or taking it out. So you can take that information and you can make a phase diagram like this, where pressure versus temperature shows you, for example, that the lines are where you have 2 phases in equilibrium. So on the right-hand side, we have a liquid-gas equilibrium line. On the right-hand side, we have a solid liquid. And if we're below the thing called the triple point, that's the line where solids in equilibrium with a gas. The critical point is a point at which you no longer see a phase transition. So it's where liquid can't be compressed to gas beyond that temperature and pressure. It's easier to look at this one and think about it where they actually have temperatures. So with water, if you're at high temperature and low pressure, you're going to have water vapor. You're going to be in that tan region. If you have moderate pressure and temperature, you're going to be in the liquid region. And if you're at a low temperature, you're going to have a solid. If you're below B, B is the point at which liquid, solid, and gas are all in equilibrium. It's called the triple point. So you could figure that out with your cooling curve. And if you're below that, then you will only be able to sublime the ice into gas. You'll note at those low pressures, you'll never see liquid water. So we're above the triple point at normal atmospheric pressure. Remember, that's about 105, 101, I guess, 101 kilopascals. So that shows us that the normal melting point is 0 degrees. The normal boiling point is 100 degrees. The critical point is at 374 and 22,000 kilopascals. What else can I say about this? And along that line, so if you look at the line from B to C, this equation would allow you to calculate points on that line. And if you notice, it looks pretty logarithmic going from B to C. So essentially those points, which phase diagrams are usually created from experiments, but you can also confirm with theory that a line between, whoops, not this one, B and C. This is just an example of the idea of freeze drying. So this idea that when you're below the triple point, something will sublime. So if you freeze it, you can take the water off of something like ice cream if you're below the triple point. And this is just another way to understand what the phase diagram's telling you. So with water, water is unique in that the solid liquid line is a negative slope. So that means if I'm, for example, at 0 degrees and I start out at low pressure and I increase the pressure and I have a solid, I'm going to cross over the line at which it goes into the liquid phase. And so that's because ice has a lower density than liquid water does because of the really ordered structure of ice. And that's very uncommon. So water is one of the only substances where that would be the case. In general, that line will have a positive slope, which would mean if you have a solid at a temperature and you increase the pressure, you're just going to keep it in that solid phase because the solid is the more dense. So when you look at why a glacier moves because under all that ice, there's a lot of pressure. And so the phase diagram shows us that if you apply pressure, it forces the ice into liquid phase. And so essentially, then it can move because you have that slippery liquid water underneath it. This is a phase diagram for carbon dioxide. It's much more complex than water. The shape of the lines are more complex, but it's the same idea. You have a triple point, you have a solid, liquid, gas, you have a supercritical fluid. So that's the fluid when you're above the point at which the liquid gas line ends. That's the critical point. But notice that the solid liquid line is slanted positive. So that means if you have some solid CO2 and you apply pressure to it, you're just going to keep it in the solid phase because solid CO2 has a greater density than liquid CO2. This one, I just never could quite figure out what they are showing with those green and red. If you figure it out, you can come and tell me, but I've never seen this in another book and it just didn't make any sense to me. Okay, this is just talking about what that supercritical fluid up above the critical point behaves like. And it's a really good solvent. So presently, supercritical CO2, so CO2 that's up in that green region of temperature and pressure, is used to take caffeine out of coffee. Because the really nice thing is that it then just vaporizes. And so you don't add any toxic chemicals to your coffee. Used to be that we used chlorinated solvents to remove caffeine from coffee. And there was always residual chlorinated compounds in there, which are carcinogenic. So it's good that they found a use for CO2 that would improve our health. So this is our last section, the solid state of matter. We want to talk about the bonding and the properties of ionic, molecular, metallic, and covalent network crystalline solids. We want to describe the types of crystalline solids, ionic solids, metallic solids, covalent solids, and molecular solids. And we want to explain the ways in which crystal defects can occur in a solid. So crystalline is where there's a nice ordered packing arrangement. Depends on the size of atoms or ions, but this one is where you're looking at, must be a metal where all of the atoms are exactly the same, versus amorphous. Glass is amorphous, for example, so it's packed into a solid, but it's not ordered. And so when we look at silicon dioxide, which is sand, it's a very, very ordered structure on the left-hand side. When it's in sand, it has these hydrogen bonds. No, it doesn't have hydrogen bonds. It just has strong dipole bonds between the oxygens and the silicon. Versus on the right, it's amorphous, so it's not as ordered, and that's the form it takes when it's in glass. So when we talk about ionic compounds, they form these really nice ordered packing structures. So the purple and the green are representing the sodium cations and the chlorine anions. And you'll notice that there really isn't just a sodium chlorine ionic bond. The whole thing has cations and anions completely surrounded by the opposite. This is a metallic sample of copper. So it's where the atoms are all packed tightly together. That's a crystalline structure. And these are showing you some network covalent bonding. I'll bring into class a demo of carbon and graphite because it's really nice to see it. This picture of diamond's not very clear. The big difference is that in diamond, each carbon has sp3 hybrid orbitals, so it forms 4 bonds, whereas when it's in graphite, it has sp2, so it forms these planar sheets, and then graphite is held together with dispersion forces between those sheets. So it's really soft. It's actually what your pencil lead is. It's graphite, and so those sheets come off easily, whereas diamond is the strongest substance there is because you have to break covalent bonds in order to take a carbon atom out of a diamond solid sample. The other two in the middle are samples. We already looked at silicon dioxide, which is sand, and then carbon or silicon carbide has also the network covalent structure. So network covalent means that your system is really a large covalent molecule. It's not a whole bunch of small covalent molecules held together by intermolecular forces. So these are 2 pictures. So carbon dioxide is polar. So you're going to have more structure in how the molecules sit next to each other. Oops, carbon dioxide is not polar. I'm sorry, I was thinking of carbon monoxide. So that's why the structure does not look very ordered. I also have a model for that I'll bring to class. So both iodine and carbon dioxide are just molecules that have London dispersion forces. They're non-polar, so they're not really going to pack in a constant, steady, organized way. And these are just showing you those structures and how they contribute to diamonds' very stable situation, and graphite, which is your pencil lead. Graphene is another form of carbon that was only discovered in about 2000. And so graphene is actually taking graphite and removing the sheets from each other so that you have single sheets. And when you look at those sheets, they're all sp2 hybridized carbon. And so the sheets are super, super strong. So you can use them to reinforce things like you could steel. But they're super light because it's a single sheet of atoms. So a buckyball, a nanotube, and then these stacked sheets make graphite, and a single sheet is called a graphene sheet. And when you look at those packings, you can see that based on the size of your atoms, you may have other atoms that could fit into that structure. So the interstitial impurity, that's something that's small enough to pack in, even if your structure doesn't have a hole. You can also have a defect that's called a vacancy, which just makes sense. You have a place where you just happen to not pack an atom for some reason. You can also have substitution impurities. So you can have a red atom in there if it's about the same size, and then another substitution impurity that's not the same size, so it causes a greater disruption in the packing. But each of those defects can change the properties of that solid. So for example, when you're talking about photovoltaic panels, they usually have impurities in the silicon structure, which help with the conductivity. So that is the very last slide that we will talk about in this class. So that's the end of chapter 10.